What if I told you that a space rock we just discovered 2 days ago zoomed past Earth today, at a distance closer than the Moon? An asteroid called 2025 TP5 made a near miss, flying by at just about 60,128 miles, 97,089 Kelvin, roughly 1/4 of the lunar distance. It's close. But don't panic. It posed no threat. Yet this event is a vivid reminder: the cosmos is full of surprises. Join me as we unpack how we discovered this asteroid so late, what we know about it, how astronomers track such objects, and what lessons we draw for planetary defense. On October 13, 2025, astronomers first spotted this asteroid using the ATLAS system, Asteroid Terrestrial Impact Last Alert System, located in Mauna Kea, Hawaii. The detection was made only about 48 hours before its closest approach, a tight window by space standards. The discovery was reported to the Minor Planet Center, MPC, which handles the cataloging and sharing of new object observations to the scientific community. The goal: confirm the orbit, compute the trajectory, and assess any threat. In this case, scientists found it would fly safely past Earth. Interestingly, this is not unusual. Many small near-Earth asteroids are only discovered hours or days before a close approach. Our detection systems are good, but not perfect. At 4:09 p.m. EDT, 2009 UTC on October 15, 2025, TP5 passed its closest point to Earth, about 60,128 miles, 97,089 kilometers away. To put that into perspective, the Moon orbits at an average of 238,155 miles, 384,400 kilometers. So this asteroid was about 1/4 the distance between Earth and the Moon. The next day, October 16th, it also passed fairly close to the Moon, coming within 74,116 miles, 120,084 kilometers. Its speed and trajectory were mapped so astronomers could confirm it would not cross Earth's path. From observations, scientists estimate 2025 TP5 is about 54 feet, 16 meters in diameter. That's similar in size to the Chelyabinsk meteor in 2013, which exploded in the atmosphere over Russia and caused shockwaves that damaged buildings and injured people. Because of its modest size, if it had entered Earth's atmosphere, much of it would likely burn up, producing a bright fireball rather than catastrophic damage. But even small asteroids merit attention. They can illuminate gaps in our detection systems and help refine our models. So, how do scientists find, track, and assess asteroids like 2025 TP5? Several survey systems operate continuously. ATLAS, used here, is one. Others include Pan-STARRS, the Catalina Sky Survey, and future projects like the Vera C. Rubin Observatory. These telescopes scan large patches of sky nightly, looking for objects that move relative to stars. Once a candidate is detected, follow-up observations refine its orbit. Thanks to the Minor Planet Center and groups like NASA's Center for Near-Earth Object Studies, CNEOS, orbits are publicly shared and threat assessments updated. Their models compute the minimum orbit intersection distance, MAOID, and check if an orbit intersects Earth's path, adjusted for gravitational perturbations from planets. The key point: for many small asteroids, we often have short warning times. That's why detection, rapid follow-up, and prediction matter. You might ask, it posed no risk, so why cover it? The close approach is a real-world test of our asteroid detection and planetary defense infrastructure. It exposes gaps. We only found TP5 2 days before. If it had been larger or on a less favorable path, the margin would be thinner. Also, it adds to our statistical record of near-Earth object, NEO flybys, helping us understand their frequency, size distribution, and orbital behavior. This helps refine how much telescope coverage we need, where to prioritize investments, and how to improve early warning. Close flybys aren't rare. In fact, astronomers track many of them each year. For example, earlier this month, another asteroid, 2025 TF, passed extremely close, in some cases just hundreds of kilometers above Earth. The difference, many are small and harmless, and most are detected after their closest approach. Scientists also study how asteroids spin and respond to solar radiation, which influences orbit predictions. E.g., see How Do Asteroids Spin in Space on space.com. Also, a fascinating possibility. Some near-Earth asteroids might originate from the moon itself, ejected by past impacts, adding complexity to how we classify these objects. See research on lunar ejecta asteroids. All of these cases underline one theme: space is dynamic, and we must remain vigilant. Let's imagine a scenario. What if an asteroid like TP5 were on an actual collision course? Planetary defense plans often consider deflection techniques, such as kinetic impactors, smashing into the asteroid to nudge its orbit, or gravity tractors, using a spacecraft's gravity to tug it. But for small, late-discovered objects, the challenge is having enough lead time. That's why even spotting small asteroids ahead of time is critical. Earlier is better. Agencies globally run drills, simulations, and invest in new detection tech, space-based telescopes, better ground surveys, to improve warning time and response capability. Asteroid 2025 TP5's flyby was a close call in terms of proximity, but not danger, yet it served as a real-world stress test for our detection and defense systems. It reminds us of the dynamic nature of our cosmic neighborhood, and how much we still have to learn. As telescopes grow more powerful and sky surveys expand, we'll get better at spotting these visitors sooner and reacting appropriately. If you enjoyed this breakdown, hit that like button and subscribe. Want a deeper dive into planetary defense or more asteroid stories? Let me know in the comments. I'll see you in the next space video.